Hello? Today we're going to embark on a marvelous journey into mechanical wizardry. We'll explore a machine, a forgotten hero of sound. The vinyl recorder, the disc-cutting lathe, not a record player. This machine creates the record. It takes electrical signals and physically carves them into a blank disc. Brute force and delicate precision. How does it work? Like a potter's wheel for sound. Spinning platter, a special arm that moves across it, a very, very sharp point that carves. Music feeds into the machine. The cutting head vibrates precisely. Those vibrations guide the stylus to etch a microscopic groove. The groove is a wiggly physical representation of the sound wave, a mechanical photograph of music. Start with raw ingredients. Think of a complicated engineering cake, high-quality metals, a testament to human ingenuity. The first major component we need to build is the platter. This is the heavy, rotating disc upon which the blank record will sit. You might think it's just a simple turntable, but its job is critically important. Its primary function is to spin at a perfectly constant speed, usually 33 1/3, or 45 revolutions per minute, without any hint of wobble or vibration. Any variation, even a tiny one, will be permanently etched into the recording as a distortion in the music's pitch. Something musicians call wow and flutter. To prevent this, the platter has to be extraordinarily heavy and perfectly balanced, acting as a massive flywheel. The process begins with a solid billet of high-grade aluminium. This isn't your everyday stuff used for drink cans. This is aircraft-grade material, chosen for its density and stability. The billet is placed onto a giant metal lathe, a machine that spins the metal at high speed, while a cutting tool shaves material away. A skilled machinist carefully sculpts the billet into a perfectly circular and flat disc, often weighing upwards of 30 kilograms. The tolerances here are incredibly fine. The surface must be flat to within a few microns, which is thinner than a human hair. It's a slow and meticulous process, requiring immense skill and patience. Now that we have our impressively heavy and perfectly balanced platter, we need a way to make it spin. This is the job of the motor and the drive system. You might think you could just connect a motor directly to the platter, but that would be a terrible idea. Motors, by their very nature, vibrate. This vibration or cogging would transfer into the platter and be carved into your record as a low-frequency rumble. The challenge: transfer rotational force while isolating vibrations. Classic engineering conundrum. The solution: a belt drive system. Powerful, high-torque motor mounted separately from the chassis, sometimes on its own heavy, isolated base. A special belt, non-stretchable, precisely ground, made from silicone or rubber composite. Belt looped around a pulley on the motor and the outer rim of the platter. The belt acts as a mechanical filter, strong enough to transfer torque, elastic enough to absorb motor vibrations, preventing them from reaching the platter. Simple, elegant, remarkably effective. With the platter spinning perfectly, we now need the mechanism that will carry the cutting head across the record. This is the tone arm. On a lathe, it's more accurately called the carriage assembly. A close-up of the carriage assembly, highlighting the lead screw and the arm holding the cutter head. Unlike the tone arm on a record player, which is pulled along by the groove, this one has to be actively driven. It must move the cutting head from the edge of the disc to the center, in a perfectly smooth, straight line. That movement must be synchronized with the platter's rotation to create the correct spacing between the grooves. Pitch. The construction of this carriage starts with precision machining. It's typically built on a heavy, rigid track that runs parallel to the platter's surface. Upon this track sits a carriage, which glides with almost zero friction. This is often achieved using incredibly precise ball bearings, or even an air-bearing system where the carriage literally floats on a cushion of compressed air. The goal is to eliminate any stiction, that initial resistance to movement. It needs to move as smoothly as a puck on an air hockey table. The movement of the carriage is controlled by a lead screw. This is a very long, finely threaded rod connected to its own dedicated motor. As the lead screw turns, it slowly pulls the carriage along the track. The speed of this motor is what determines the groove spacing. For loud, dynamic passages of music, the grooves need to be spaced further apart. For quieter sections, they can be packed more tightly together. In modern lathes, a computer analyzes the music a split second before it's cut and adjusts the lead screw speed on the fly. It's a clever bit of predictive technology. We now arrive at the sharp end of the business, quite literally, the cutting stylus. This is the tiny, yet immensely important component that does the actual carving. It is a microscopic chisel that must be harder than the lacquer and shaped with astonishing precision. The exact geometry of the stylus tip determines the shape of the groove, affecting the frequency response and the stereo imaging of the final record. Making one of these is less about heavy machining and more like the art of a master jeweler, a task of microscopic proportions. The journey begins with a tiny synthetic diamond or a sapphire. These are industrial-grade crystals, not jewelry gems, grown in a lab under immense pressure and heat. Natural diamonds can have imperfections that might fracture. The tiny crystal, barely a couple of millimeters long, is bonded to a metal shank so it can be mounted into the cutter head. The real magic is the shaping. The crystal is painstakingly ground and polished with diamond-impregnated polishing discs. Section 6. Putting it all together, the main assembly. Now that we have all our beautifully crafted individual parts, the platter, the motor, the carriage, the cutter head, it is time for the grand assembly. This is where the machine truly comes to life. The process starts with the chassis, or the main frame of the lathe. This is an incredibly heavy, solid structure, often machined from a single block of metal constructed from thick steel plates welded together. Its sole purpose is to be a massive inert anchor for all the other components, absorbing any external vibrations from the floor or the air and preventing them from reaching the delicate cutting process. First, the main bearing for the platter is installed into the chassis. This is another component of extreme precision, designed to support the immense weight of the platter while allowing it to spin with virtually no friction or play. Then the platter itself is carefully lowered onto the bearing spindle. Next, the carriage assembly with its track and lead screw is mounted. Its alignment relative to the platter is absolutely critical. It must be perfectly parallel to the platter's surface, ensuring the cutting depth remains constant from the outside edge of the record to the inside. This alignment is checked with laser instruments and dial indicators measuring in microns. The motor is then installed in its isolated position. The drive belt is carefully fitted. The tension of the belt is crucial. Too loose and it will slip, too tight and it will put unnecessary strain on the motor and platter bearing. After the mechanical parts are in place, the wiring begins. Section 7. A bit of history. How we got here. The story of the vinyl recorder is really the story of sound recording itself. It all began in 1877 with Thomas Edison and his phonograph. His invention was purely mechanical. He would shout into a horn which caused a diaphragm to vibrate. Attached to the diaphragm was a stylus that indented a groove onto a rotating cylinder covered in tinfoil. To play it back, a needle traced the indentations, vibrated the diaphragm and reproduced a faint, ghostly echo of his voice. The first words ever recorded, "Mary had a little lamb." It was pure acoustic and mechanical genius. The next great leap forward came with Emil Berliner in the 1880s. He had the brilliant idea of recording not on a cylinder, but on a flat disc. This was much easier to store and, crucially, to mass produce. His gramophone used a zinc disc coated in a thin layer of wax. The stylus would cut a spiral groove laterally, side to side, rather than Edison's up and down method. To make copies, the master zinc disc could be used to create a metal stamper, which could then press hundreds of copies in a material like shellac. The commercial record industry was born. Section 8. The first cut, calibration and testing. Once our magnificent machine is fully assembled and isolated from the world, it cannot simply be switched on to cut a masterpiece. Before the first real groove is ever carved, the lathe must undergo a rigorous process of calibration and testing. This is perhaps the most painstaking phase of all, where the cutting engineer, a person with the ears of a musician and the mind of a physicist, fine-tunes every aspect of the machine's performance. It is a process that requires immense patience, specialized tools, and a deep understanding of the physics of sound and motion. The first step is to check the mechanical alignments again. The engineer uses a microscope mounted on the carriage to ensure the stylus is perfectly perpendicular to the record surface. They check the tone arm's vertical tracking force and adjust the depth of the cut. A test cut is then made, not with music, but with specific test tones, pure sine waves at different frequencies. The resulting groove is then examined under a powerful microscope. The engineer looks at the width of the groove, the smoothness of its walls, and the shape of the wiggles to ensure the stylus is carving cleanly and accurately. Next comes the electronic calibration. The amplifiers that drive the cutter head must be perfectly balanced for the left and right stereo channels. Section 9. Why bother? The enduring magic of cutting vinyl. So after all this incredible effort, this obsessive attention to detail, this monumental feat of mechanical and electrical engineering, in a digital age of instant streams and perfect copies, why bother? Why physically carve music into a fragile plastic disc? It seems utterly bonkers. The answer lies not just in the sound, but in the process itself, creating something tangible and permanent, undeniable magic to a well-cut record. Not perfect like digital. A particular character, a warmth and presence, subtle, often pleasing artifacts. Physical limitations of the medium force engineers to make careful artistic choices about dynamics and frequency balance. Constraints breed creativity, not a collection of data, a crafted object with unique sonic personality. Making a vinyl record is a celebration of craftsmanship, precision, the intersection of art and science.